The old resistivity logs. Now, I'm not going to go in and, like I say, I'm not going to go in and I'm going to show examples, but we're not going to calculate them because this used to be a whole week course. And back in the old days when Schlumberger, whenever they come out with something new, you know, you'd go for a week's logging course. They'd give you lunch every noon. They'd give you a cocktail party and a buffet on Friday night. Oh man, what neat they were. They don't do that anymore. But again, so in 1 hour's time, there's only so much really I can cover, but I will try to show what these are. Hope you all know them. There's a lot of these running around. Again, the long normal and the short normal. Now this is not the way it's done on many of the logs. So this example is not quite typical. But again, the short normal along here, the short normal is about a 16-inch. So again, it's a very shallow tool, shallow resistivity tool. The long normal is a 64-inch, approximately. They varied somewhat depending on which company they used, but it's a little deeper. The lateral curve is the one that I'll spend a little more time on. The lateral curve, now this is again not the lateral log. This is the lateral curve. This is normally an 18 feet 8-inch log. Now this is the spacing between the electrodes. And so why do we use this the most? Because of the long spacing, we can get the RT out of it, the best RT that we can get. The others are, we'll say, much shorter. But again, so this will be the one that I'll talk a little bit about. And again, the lateral curve. And again, why is this interesting? Because I'll show you in log interpretation, if you just pick one of these up, lateral log, then you can make some bad interpretations if you don't remember the 18-foot spacing. Very, very critical. Here's one illustration that I'll use here again. Here's the lateral curve over in here. Here's the short normal, 16-inch. The dotted in here, and then the solid in here is the 64-inch. Now again, this is an example of a well, of the old well anyway. So the question is, what is the RT on this? And again, if you look at this RT, this is about 12.5. If you took the highest point on this particular, on the long normal or the short normal, we're out around 12, 13 ohms. We talk about here is probably, let's say 12 ohms, something like that. Down here, we're talking about 1 ohm to maybe 4 ohms. The RO, which is, you well realize it, know better than I do, is the resistivity at 100% water. But what can we do with this? Where is the RT for calculating? One thing I ought to mention at this time, because of the spacing of these tools, these do not lend themselves so well to digitizing. Sometimes it works if you get long sections, but like John has talked about as far as digitizing, because of the spacing and the way the curves are read, you can't really do a foot by foot. Now some of them you can, and I'll show you some examples when you can, but you can't always digitize in order to do log analysis. In this case, which is the RT? And out in here, the lateral is, out in here is what about, looks like it's 9 ohms. Which is the RT? As I will try to show in the next 45, 50 minutes, who cares? I don't. Yes, here's what I say. This is 12 ohms. This is somewhere around 12 and a half ohms. This is 9 ohms. The accuracy is not that important to me. Whether you, and I will show you by plots a little later as far as using our Pfeffer plot, which was designed by the survey and is a very good tool for this type of thing. On logarithmic scale of porosity versus resistivity, it really doesn't make any difference. So I come back to the point I started out with. What is important? Why are you doing this log analysis? Now, I have sat in on some engineering programs where we're unitization. And if you have done any of the unit studies, then you realize, each company fights for 0.1% porosity. They fight for this, and you all try to get together. And the one I had was one main one was all majors. Well, we fought and argued, but you try to finally come up with a solution. And it's everybody's happy, and that's what you go with. But is it worth? So in a unitization, then you, in a sense, you want to correct for everything. You want to correct for resistivity. You want to correct for porosity, for bed thickness, and all that. But if you're doing it like most of us do it, you sit on a well, or you're doing a field study, or you're trying to get a quickie evaluation before the field is developed on how much oil it'll make. Do you really care about that accuracy? What are you after? You're after about, what is the porosity? Within 1 or 2% porosity units, in my opinion. And I will show later that's, in my opinion, the uncalibrated neutron is a great log. Has it got problems? Oh, I hope to tell you it's got problems. The resistivity, but water saturation. I mean, you want to be close, and you want to be, I'll call it accurate, but not precise. And don't, so my opinion, don't, when you do log analysis, think about it before you start. What do you want out of this? Do you want to know to set pipe? Do you want to know to plug it? Do you want to put the perforations? What do you want to do with it? Do you want to acidize? On and on and on. But you do not need at that time sitting on the well or immediately thereafter to be exactly right, because that's all you'll do in your whole life. So in this particular case, again, here would be the SP on this particular one. And as it was brought out this morning, one of the things you can do with the SP, which is great, if you don't have the RW, you've got to, in order to do the Archie and be able to analysis, you've got to have RW. But again, what do we see out of this? Just immediately looking, we see that, hey, assuming this shale does not separate two different pays, then immediately here's more resistive, like we talked earlier today on the gentleman that you want good porosity and you want better porosity and more resistivity, then obviously this is interesting. This is interesting. Look at the transition point down to here. Here's RO at 0.4 ohms. Here surely is water. So water here is oil, and here will be your transition zone. So in this particular case, you could do, in my opinion, you probably could take these numbers and use them for, again, digitizing to come up with where is the oil-water contact about. The SP, it was covered quite a bit this morning. I won't take a lot of time, but again, the part that's interesting in the old logs is, I'll skip this one, you can get that out of the book. Again, it's a relative relationship between the RMF, the mud filtrate, and the RW. And it's whether one's larger, one's smaller, determines what is your SP. Now again, as I mentioned, you can get the SP, you can do your RW off of it, but you also can do some bed work as far as. If the RMF is less than the RW, and remember, I think it was Richard that mentioned the average in Kansas of RW is about 0.04. That's what I always use when I start out. If I don't know, I'll use a 0.04 and then I'll go from there and adjust. So if we say RW is 0.4 and RMF is less than that, then you get, it's a deflection to the right, it's a reversed SP. This will be your freshwater sand. These will be your freshwater, usually more shallow. If the RMF equals the RW, you get no SP. It'll be a straight up and down. I'm going to show you a slide in a second to show that. If RMF is much greater than RW, which is in most cases, because again, even when we get to the salt mud surveys, usually RMF is more than 0.04 or 0.03, which is the typical RW in, I'll say, use Kansas as an example. This will be the normal SP.